Hey guys, I am back for the next chunk of this, going through questions 4 through 7. Although this is rather thin because there's lots of Unit 8 and 9 stuff in questions 5 and 6. So it will be pretty quick, way, way, way quicker than the previous video. So I apologize for the half-hour monster that I just released, but it is what it is. Okay, so number 4. They have two molecules for us. They have CS2 and they have COS. They have pictures of those, and they're both linear molecules with carbon in the middle. The one has a sulfur on either side, the other one has an oxygen on one side and a sulfur on the other. And so, part A here is asking, in terms of the type of relative strengths and of all the intermolecular forces in each compound, explain why the boiling point of CS2 is higher than that of COS. Now, this is a mean question. The 2018 test, by the way, I think was way worse than the 2019 test, if you haven't figured that out yet. This is asking about intermolecular forces, and they give us some data. The data they give us is that the boiling point of CS2 is higher than COS. What that's trying to tell us is that the strength of those intermolecular forces are stronger than the strength of COS. Now, the hard part with that is that if you look at the structure of those, CS2 is a linear, nonpolar molecule, meaning the only type of intermolecular forces that that molecule has are London dispersion. COS is linear but polar. So that molecule has London dispersion and dipole-dipole forces. And I've told you that dipole-dipole is generally stronger than London dispersion, and that's absolutely true. But that's not what they're looking for here at all, because they have given you the answer. What they want is the explanation. In other words, they're telling you that CS2 is a higher boiling point than COS, and they want you to explain why. Now, that sounds extremely difficult on the surface because everything that I've taught you is giving you the opposite, right? If the boiling points weren't there, I think we would make a prediction that COS is a higher boiling point than CS2. And I think AP would expect us to make that prediction. But they've told us that that's not the truth. So now what we need to do is justify why it's opposite. And it's not a profound explanation. We're not going to go very deep into it. All they're looking for us to do here is to say, okay, this molecule has London dispersion, this one has both London dispersion and dipole-dipole, but based on the fact that CS2 has a higher boiling point, the strength of the London dispersion forces of that molecule must be greater than the strength of the combined dipole-dipole and London dispersion forces of COS. That's it. That's all we can really say. That's all they want you to acknowledge, is that the intermolecular forces must be stronger in CS2 than in COS. Now, again, this is a completely counterintuitive question because what I've taught you and what we've talked about would have led us to predict the opposite. But once the answer's been given to us, there's no longer a prediction that needs to be made. All that we need to acknowledge is that the strength of the CS2, it has to be higher than the strength of the COS in terms of intermolecular forces. Weird, kind of a weird question. Part B, a 10-gram sample of CS2 is put in an evacuated 5-liter rigid container. The container is sealed and heated to 325 Kelvin, at which temperature all of this CS2 liquid is vaporized, meaning it's 100% turned into gas. What's the pressure inside the container once this has all been vaporized? Okay, so we've got a volume, we've got a temperature, and we've got a mass. Now, mass isn't moles, but we've got 3 parts of the ideal gas law. First things first, we need to figure out how many moles of gas this will be, and then plug that in to our PV equals nRT. So 10 grams of CS2, we use the molar mass of that off the periodic table to convert to moles of CS2. And then we plug in the volume that was given, the moles that we just calculated, our value of R, which is the gas constant, which is in the formula packet, and the temperature. Plug all that in, you get a pressure of 0.701 atmospheres for part B. And that's question 4. Again, these 4 through 7 are the short ones. You notice the first 3 were pretty monstrous today. And these next ones are pretty short. And again, we'll run into some spots where we're going to skip over a whole bunch. But that's question 4. Question 5. We have a hydrofluoric acid, HF. They show it reacting with water in an equilibrium, dissociating and producing F1 minus and hydronium H3O1 plus. So they tell us the ionization of HF in water is represented by the equation above. In a 0.035 molar solution of HF, the percent ionization, or in other words, what percentage of it breaks apart, is 13%. They give us two pictures or two representations of HF. Explain why the representation of the ionization energy of the ionization of hydrofluoric acid in figure 1 is more accurate than figure 2. Okay, so let's look here. Figure 1 shows a whole bunch of HF molecules and one of them broken apart into F1 minus and hydronium. Figure 2 shows every single molecule dissociated. And here's the deal. They told us that 13% of this breaks apart. Here's the other deal. If you recognize HF, that's not one of our 6 strong acids. It's a weak acid, meaning it shouldn't dissociate very much at all. So we have an undissociated representation of HF, and we have a dissociated representation of HF. Well, this one's better. And the reason why is because HF is a weak acid, and not only that, they told us it was only supposed to be break apart 13%. That's way more than 13%. That looks like 100% to me. So here's my answer. The first picture represents HF as very slightly dissociated, whereas the second picture represents HF as fully dissociated. HF is a weak acid, and it dissociates 13% according to the introduction. So picture 1 is better. Easy as that. Part B, use the percent ionization to calculate Ka. That's unit 8. We're skipping it. Part C, if 50 milliliters of distilled water was added to 50 milliliters of the HF, what will the percent ionization of HF increase, decrease, or remain the same? That's unit 8. So we're not going to deal with that either. Question 6. You've never seen anything like that in your life? Guess what? That's unit 9. And every single one of these relates to unit 9. So this is talking about a galvanic cell and the potential and the voltage of that and half reactions and redox. Yep. Nope, we got none of that. Calculate the cell potential. That's unit 9. We could write a balanced net ionic equation. We could do that. But really, it's without the context, it's probably not much use. And in reality, it's pretty simple. Anyway, part 3 of that is asking for Gibbs free energy. That's unit 9. So question 6 is kind of irrelevant for our purposes. So onward and upward. Question 7. We have a PES. This is a photoelectron spectrum. And they tell us it is, which is nice. Again, in a PES spectrum, the y-axis here is your nucleus. And as you go outward from there, you're hitting all of the orbitals in order. So this would be 1s, 2s, and then 2p is the taller one here. Again, the height of the peaks represent the number of electrons. So this is 2 electrons, and this is going to be 1, 2, 3 electrons. So we have a total of, it looks like 2, 4, 7 electrons in this. Part A, what's the element? Well, an element with 7 electrons is nitrogen. Part B, calculate the value of the rate constant. For the radioactive decay, include units in your answer. A radioactive isotope of the element decays with a half-life of 10 minutes. So we have an equation. There's an equation in your formula packet for half-life. T1 half equals 0.693 divided by K. We know what the half-life is. It's 10 minutes. 0.693 is a constant in that expression. All we don't know is K. We can flip these two spots, right? I can switch K and 10 minutes with one another in that equation. And I get 0.693 divided by 10 equals 0.0693. Now, they're giving a point for the unit in this question because it says include units in your answer, meaning it's really, really important. So when you do this, this is going to be a first order reaction. Again, it's first order because all of the half-life problems they ask you are first order. And all we're doing is taking a unitless number divided by minutes. So the label is going to be 1 over minutes. Or you could write that as minutes to the negative 1 power. That works too. But that's what we got. Part C, if 64 atoms of the radioactive isotope are originally present in a sample, what is the expected amount of time that will pass until only 1 atom of the isotope remains? Show how you arrived at your answer. So we're going from 64 down to 1. There's an easy way to do this and a more complicated way to do this, but they both work, and I'll show you both. 64 to get to 1 is going to be 6 half-lives. Hang with me. 64 to 32, 32 to 16, 16 to 8, 8 to 4, 4 to 2, 2 to 1. Okay? So we have 6 half-lives. And how long was each half-life? Each half-life was 10 minutes. Sweet. 60 minutes. Okay, that works for an explanation. The other way we can do this is if it's half-life, it's first order. And if we're dealing with time and trying to solve for time, you can use the first order integrated rate law, which looks like this. The natural log of the concentration at time t minus the natural log of the concentration at time 0 equals negative kT. Well, we don't have concentration, we have atoms, but those ratios are the same, so we can plug those numbers in. So the natural log of the 1 atom at the very end minus the natural log of 64 atoms at the very beginning should equal negative 0.0693, which is our value of K, which we solved for previously, times T. You plug all this in and you get 60 minutes, just like I had explained using the easier method. So what's really important about that one is obviously recognizing that if half-life's involved, it's first order. That's it has to be. They don't give you any other type of half-life problem. So the half-life question previous to this was a dead giveaway that we could use the first order integrated rate law. Yeah, and that's it. So that was much quicker. Again, if you have any questions on this, please let me know. I'll be doing office hours very shortly here, and yeah, hope to see you guys soon.